Hi everyone! In this video we're going to jump into section 10.3 and talk about what's called the integral test. So this is going to be a test that you can use for figuring out if a series diverges or converges. So before I give you what that test says, let me remind you of something and then tell you about a new corollary. So a couple sections back we learned this theorem, the monotonic sequence theorem, and let me just remind you what it says because both of these kind of guide us into the integral test. If a sequence, a sub n, is both bounded and monotonic, then the sequence converges. Okay, quick reminder, a sequence is bounded if it's both bounded from above and below. Okay, so if there's some kind of boundary that it doesn't go up like above, and there's some boundary that it doesn't go below. So bounded means both above and below. Monotonic, if you remember what that means, it was strictly increasing or strictly decreasing or staying constant. So it's not like going up or down. And so those two things are true, making the sequence convergent. Now a new corollary to this theorem, so like an additional consequence of this theorem, says that a series, a sub n, remember really quick with series, it's when you're adding the terms, so this is our summation notation, for the terms from 1 to infinity, of non-negative terms converge if and only if its partial sums are bounded from above. So this one is saying that if you have a series where the terms are not negative, so they're positive or zero, so if that's your series, it is going to have its partial sums are bounded from above. Or exactly the opposite, that's what the if and only if means. If its partial sums are bounded from above, then this series must have non-negative terms that converge. Okay. Now, partial sums, quick reminder about that. That's when you start adding the terms of the sequence, but you stop at some n value. So the first 4 terms, you would add that. That would be the fourth partial sum. Okay. So if it's partial sum, so all of them are bounded from above. Now I just wanted to show you these two because they're going to lead into what we're going to go over right now, which is the integral test. Okay, here's the integral test. So let the sequence be a sequence of positive terms, and then suppose that a sub n equals f of n, where f is a continuous, so you'll see where we're going with this. F is a continuous, positive, decreasing function of x for all x greater than or equal to some capital N. So before I tell you the rest of this theorem for this test, we're going to be rewriting our sequence in terms of a function. Okay, so the function f has to have the following characteristics. It has to be continuous, it has to be positive, and it has to be decreasing. So if that's true, then what's interesting is that the series, the summation from n equals capital N to infinity of a sub n, that series, and the integral from capital N to infinity of f of x dx act similarly in terms of convergence or divergence. So both the series and the integral converge, or both the series and the integral diverge. So what this test is going to allow us to do is take a series, find a function that corresponds to it, integrate that function, and then based on what we get from that integral, we can tell whether or not the series converges or diverges. Okay, so let's get into our first example. Here's our example. Does the series of 1 over n squared, from n being 1 to infinity, converge? Okay, so let's see if we can use our integral test. First, let's identify what is our sequence that makes up this series. Our sequence is made up of the terms 1 over n squared. Now, n goes from capital N until infinity. So the starting point is at 1. So capital N is actually 1. So let's relate that to a function. So our function, f of x, is going to be 1 over x squared, and then from the integral test that we wrote down, that theorem that is the integral test, we had the criteria that x had to be greater than or equal to capital N. And so for us, that means x is greater than or equal to 1. Now, I mentioned the 3 things that this function had to have true about it, so let's just make sure that's true really quick and then go forward if it is true. So one of the things was, is this function continuous? And for this, you can kind of just do a little observation. If you know what the graph would look like, or if you do graph this using a graphing utility, you'll be able to tell from the graph, but let's just observe. Starting when x is 1, if I start plugging in 1, and then 2, and then 3, and so on, then this is always just going to be a continuous function. There will be no gaps. So here's an example of like where there would be an issue. If I plugged in 0, 1 over 0 is undefined, but we're starting at 1, so not a problem. Okay, so far this function is in fact continuous. Now it also needed to be positive. Are the terms positive here? Well, again, starting at 1, if you just think about plugging in 1, you're going to square it and get a positive number. 1 over a positive number is positive. Plug in 2. 2 squared is positive, 1 over that is positive, and so on and so on. Even if you plugged in something negative here, which we're not, because we're starting at 1, it would still turn positive because you're squaring something negative. But we don't have to worry about that. This one is just positive starting at 1. It would be positive everywhere, but we're starting at 1. And then last is it decreasing. So if you had a picture of the graph of this function, you would look for, does the graph go down toward the right? Okay, that would be visually how you could tell if it's decreasing. But we're going to just do some small observations with some terms, and then you'll see that it's decreasing. So let's just pick x equals 1 and go from there. Pick a few values. Let's go do 2, let's do 3, and see if we can observe enough from this. So f of 1, if I plug that in, I get 1 over 1 squared, which is 1. F of 2, 1 over 2 squared, which is 1/4. F of 3, 1 over 3 squared, which is 9, so 1/9. And you could see what's happening if I keep picking values. These are getting smaller. So as I increase my x value, so I would be like moving to the right if I were to graph this, my x numbers are getting larger. My output values are actually getting smaller. So as I go right, the graph will be going down. And so the next one would be 1/16 and 1/25 and so on. So it's getting smaller. So it is in fact decreasing. Okay, so we just wanted to check that so that we know for sure we can use this integral test. So let's go ahead and say, okay, let's apply the integral test. So the integral test says that I can equate this series or how it behaves as far as convergence or divergence with this integral. So the integral starting from n and then goes to infinity of f of x dx. And so for us, that means we're going from 1 to infinity, and this integrand is 1 over x squared dx. Okay, at this point in this problem, it's just an integration problem, okay, for this. And then at the end, we'll just conclude what happens to the series. So for now, you're going back to your integral skills, and you say, how do I integrate this? Well, the first thing I want you to notice is that this is an improper integral, which we covered a few sections back. I think section 8.8. So improper integral. So we're going to go like this. We're going to rewrite this, and we're going to take a limit, okay, as b. So our upper limit is going to be rewritten as b. The limit is b approaches infinity. So that's how we address this improper integral. We're still starting at 1, and I'm going to go ahead and save some time and just jump into the next step where I rewrite this integrand with a negative exponent. And then let's keep going. So using our power rule for integration, let's keep this limit in the front. Limit as b goes to infinity. This is going to be x to the negative 1 over negative 1, evaluated from 1 to b. Okay, let's keep going. Let's rewrite this. We have our limit as b goes to infinity. This is going to be, and I'm going to rewrite this and plug in b at the same time. Actually, let me show you what this is going to look like. It's just going to look like negative 1 over x, because I bring that x down. Since it has a negative exponent, when we bring it down, the negative comes off on the exponent. So this is going to be negative 1 over b minus, because we subtract when we plug in our lower bound, minus negative 1 over 1. Okay. So just evaluating this term right here from b to 1. Okay, and let's simplify this, make it look a little bit better. We could factor out a negative if we need to. I'll go ahead and do that. I'm going to factor out this negative and say the negative 1 times the limit as b goes to infinity of 1 over b. Okay. Minus, I'm factoring out that negative and this negative, so minus 1. Okay, and then now we know about how this behaves. You can think back about when you were to plug in a very large number at the bottom of a fraction where when the top is staying the same, the bottom's growing, the top is not. This is like 1 out of a huge number, which is basically nothing. So this term approaches 0. Okay, and so what we get is that this becomes, let's bring that negative back in, this is just positive 1. Let me move down. Positive 1. Okay, so this integral value, we got a value out. We got a number out. We know what this is. Okay, this doesn't grow, like go to infinity or anything else. Because we got a value out like this, what that tells us is that this integral converges. Okay, because we got some number like this. So then we can conclude that our series converges. Okay, so let me just write that so that it's very, very clear. Okay, we can say, since this integral from 1 to infinity of 1 over x squared dx converges, okay, we got a nice number out of here, we can say by the integral test, then our series that we were interested in, 1 over n squared, also converges. So that's the real conclusion, this part here, that the series converges, and we use the integral test to prove it. And that's how that one works. Okay, so we'll actually let me sum this up because this is a particular type of series, and in the future when you see a series that looks like this, you'll be able to tell really quickly whether it's going to converge or diverge. So in general, that type of series we just saw, it comes up often, so we can talk about it specifically when it comes up in this format. So in general, the series, when we go from n is 1 to infinity of 1 over n to the p power. So it's 1 over n, but n has some exponent on it. This is called the p series. Okay, so this is a specific named series, the p series. And what we know about the p series is that it converges if p is greater than 1. Okay, so if the exponent is bigger than 1, like our last example, we had an exponent of 2, and we found out it converged from the integral test, the series will converge if the exponent is bigger than 1. So if this is 300 or some other number bigger than 1, it's going to converge. And so it diverges if p is less than or equal to 1. So the series will diverge if the exponent is less than or equal to 1. Now your book does go into a nice proof for this and an example for it if you are interested in how we got those two pieces of information. The last note for this one is that when p is exactly 1, so under this case here, but it's exactly equal to 1, that series looks like 1 over n, the summation of 1 over n. And this one has a special name. It's called the harmonic series. Harmonic series. And so we've seen this sequence before. We've seen this sequence, so remember sequence, I would leave off this summation, I would just focus on the sequence. We saw that the sequence converged to 0, but the series, when I add up the terms by this fact here, it actually diverges. So the harmonic series diverges. And I'm emphasizing this because you're going to end up using this one or seeing this one quite often. Alright, so we're going to get into a couple more examples. Next example. So determine if the series converges or diverges. We have the series from 1 to infinity of n times e to the negative n squared. Okay, remember e is our exponential number. It's just a number. It's about 2.718. If you know pi is a number. It has a symbol associated with it. E is similar in how we reference it. It's an exact number. Okay, so e is just a number. All right, let's go ahead and identify the sequence associated with this series. So the sequence would be this here, but let me rewrite it. We do have a negative exponent, so we're going to move that to the denominator and take off the minus sign. And our starting value for n is capital N, which again is 1. It's going to be 1 often, but not always, but I'm just making sure I mention it. It is 1. Then our function associated with this sequence is x over e to the x squared, and that's where x was greater than or equal to capital N, which is 1 again. Okay. Now let's quickly identify if we can use the integral test. Well, I'll just tell you right now we're going to be able to, but let me just verify with you. So is this continuous? Yes. No matter what I pick for x, especially starting at 1, but it doesn't really even matter. It could be any value. If I pick anything for x, there's no gaps, there's no jumps, no holes, nothing crazy. Any power on e is going to be a real number. It's just like 2.718 to a power. It's always going to work out. And then that's usually the issue. The denominator, you don't want to divide by 0, things like that. So yes, this is definitely continuous. Is it positive? Okay. Well, if we're starting at x is 1 and going up 2, 3, 4, and so on, the numerator is going to be positive numbers. And any exponent here that I square, it's going to be positive. And when I take e, which is positive, and I raise it to some powers, it's going to stay positive. So everything here is positive. Okay, so positive. And then is it decreasing? So you could plot this graph and you would be able to tell from the graph, but let's just identify with a few points just to prove it to you. So let's do f of 1 again, like we did in the last example, f of 2, f of 3, and see if we can tell enough from that, just from those 3. If not, we'll pick a few more. Now if I plug in 1 here, I did actually, you should use a calculator here because you have to have e to some power. If you plug in 1, you're going to get 1 over e, actually let me put it exactly, it's going to be 1 over e to the first power, and that's about 0.4. Okay. If you plug in 2, that's going to be 2 over e to the 4th power, because you're squaring that there, the 2 squared on bottom, and that is about, let's see, 0.4. Then if I plug in 3, that's going to be 3 over e to the 9, because I'm squaring the 3 there, and that is approximately 0.0004. Oh, sorry, I said it, but I think I wrote it wrong. 0.04, and this one has 0.0004. And you could keep plugging in, but you're going to see that these numbers are getting smaller. So as x increases, the output, the y, decreases, so the function is going down to the right, it is decreasing. Okay, so just wanted to prove it to you real quick, but the function is decreasing, and so we can go ahead and go forward, that says decreasing, and use the integral test. Okay, so our integral looks like from 1 to infinity, starting at 1 again, of f of x, which is x over e to the x squared dx. Okay, and again, this is now an integration problem. It is a series question, but we're jumping into integration, and we're working on integration, and then we'll go back and say something about the series. It is an improper integral again, and so we have to change this and take the limit as b goes to infinity. Everything else is going to stay the same here. And now I want you to think about it really quick. What kind of integration technique is going to work here? Okay? And hopefully you see it. If I let x squared be u, the derivative is present. It's x dx. Yes, there's a 2 there, but the number doesn't make us have to avoid u substitution. U substitution actually works here. So let me change colors here. U, if we let x squared be u, then du, this derivative would be 2x, and then dx. So if I solve for dx, we would get, actually I'm not even going to solve for dx, I'm just going to get rid of this 2 because we have an x dx. So if I divide by 2, I have 1/2 du is the same as x dx. And the x dx is present, so this is good. So then we have our limit of our integral as b goes to infinity. Now I want to be really clear here. We are changing our variable to u, so I'm going to be clear that this is x. X goes from 1 to b. So I'm not plugging in 1 and b for u later. I have to go back and write it with an x. And this is now going to be x dx is the 1/2 du, okay? So it's just going to be 1 over e to the u, and then x dx is 1/2 du. All right. And then this integration, we've seen this a number of times. We can do this one pretty quick. So we have, let's go ahead and we can factor that 1/2 out to the front of the integral or all the way in front of the limit here. I'm going to go ahead and go all the way out in front of the limit. 1/2 the limit as b goes to infinity, integral of from x equals 1 to b. I'm running out of room. It's getting a little tight here. And this is e to the negative u du. And then if you need to, you can use u substitution here. Now you can use u substitution if you need to, but if you see it, you're just going to have an extra negative. I'll just show you really quick. I wouldn't call it u again, maybe w. If I said w is negative u, then that derivative would be negative du. So I would just have an extra negative when I integrate this, because we know the integral of e to the x is e to the x. We're just keeping an extra negative there because of this substitution. Okay, so let me actually move up here so we have some more space. And continuing, we have 1/2 times our limit, b goes to infinity. This integral is negative e to the negative u. Negative e to the negative u, and then x is from 1 to b. Okay, keeping it clear that I didn't change my limits of integration. I could have solved for u back here, but I'm just leaving them. I'm going to resubstitute. Okay, so let me go right here and rewrite. Okay, I'm just showing every step, but you might have been able to maybe jump maybe from here to right here where I'm about to. This is negative e to the negative x squared. Okay, and then we're plugging a 1 to b. Now let's just make this look a little better. I'm going to move this to the denominator because that negative exponent, and then keep going. Alright, so we have 1/2 our limit. Actually, let's bring that negative all the way out front. Negative 1/2. This is going to be 1 over e to the positive x squared, evaluated from 1 to b. And I'm just showing every single step, but feel free to like go from here to where I'm about to, the next step. Maybe if you're able to, you could skip this one. So negative 1/2, our limit, b goes to infinity, of 1 over e to the b squared minus, that's going to be a 1 there, 1 over e. Okay, because we plugged in 1 and squared it for that exponent. Okay, now take the limit on so this is a constant. This is like 1 over 2.7. Okay, but this one you have to plug in very large numbers for b. And think about what happens if I take 2.7 ish and plug in something really large, square it, and that becomes the exponent. This this denominator is going to get really big. This denominator is going to grow, but the top is going to stay 1. So it's like 1 out of a huge value, which is basically like nothing. So this term right here, again, is going to go to 0, like the previous example. So this becomes negative 1/2 times negative 1 over e. So 1 over 2e is the answer. Okay, so that's not the end of the problem. I don't say, okay, I'm done. I have to relate this back to my my series. This integral, when we started, this was our integral value. It converged. This is a value. This is a number. This is 1 over 2 times 2.7, roughly. So this is a number. So because it equals some value, this integral converged. So we can say something like the last one. So since our integral, let me move that out the way, from 1 to infinity of x over e to the x squared dx converges, then we can say that our series converges. So then our series from 1 to infinity of n times e to the negative n squared also converges. Okay. And that is another example of our integral test. Let's go ahead and do one more. Okay, let's try this example. Same idea. Is this series going to converge or diverge? So this time we have 1 over 2 to the ln of n power. So the natural log of n is what that says. So 1 over 2 with the exponent is natural log of n. And n is going from 1 to infinity again. Okay, so our sequence associated with this series is 1 over 2 to the natural log of n, where n starts at capital N, which is 1. And so our function associated with this sequence is 1 over 2 to the natural log of x, where x is greater than or equal to capital N, which is 1 again. Alright, I won't go through the is it continuous, positive, and decreasing. I've shown you how to do that. Hopefully that makes sense. So I'll just tell you it is. It fits all those three criterion that it needs. So we can go ahead and go right into our integral test. I'm also going to jump right into the fact that I know it's an improper integral. So I'm going to put the limit on already because I know my upper bound was going to be infinity. Okay, so I went ahead and just jumped one step ahead. And instead of putting infinity here, I went ahead and put the limit already. And so our integrand is 1 over 2 to the natural log of x dx. Okay, so again, now this is an integration problem. So how do I integrate this is what I'm asking myself. How do I integrate something like this? And this one's a little interesting because the exponent has x in it, but it also has natural log. So what we're going to do here, we're going to try u substitution. Let's see what happens. So we're going to let ln x equal u. Okay. So then let's see what that tells us about du. Then du, this derivative, is just 1 over x, and then dx. Okay. So if I times both sides by x, I get x du equals dx. Well, if I look back at my integrand, if I put the u here, my du is not there, okay? Du has a 1 over x. And if I substitute for dx, I'm going to introduce an x that wasn't there already. So I can't leave things in terms of x and u. It has to either all go to u or all stay in terms of x. So the fact that this x du would be in this integrand, I have to address that. And here's how. I'm going to go right here and say, well, if I know how u relates to x, u is natural log of x, can I find x? And I can. So let me go back to logs with you for a second. So remember what logs are talking about. So quick side note on algebra. We have log base e of x equals y. Okay. Log base e is what ln is. Natural log. So we tend to not write log base e, we say ln. So ln x equals y is what this says. And by definition of what logarithms are discussing, what they're about, is they're about the exponents. This says this base e to this exponent equals this argument right here. Okay. When you learn about logs, it's because, really quick, it's because you just learned about inverses, and this is the first way how you learn how to find the inverse of a function where you're solving for the exponent. So logs allow you to solve for exponents. Logs equal the exponents. Alright, so ln x equals y means base e, this is the exponent. It equals the exponent on e. So back here, that's telling me that e, base e, this ln equals the exponent. E to the u equals x. Okay. So if you remembered that, that's great. If you didn't, hopefully that makes sense. And then let's keep going. Now let's rewrite this integral. So we have our limit as b goes to infinity. I'm going to specify this is x, goes from 1 to b. And this is now 1 over 2 to the u, because ln x was u. And then my dx is getting replaced with x du But instead of writing x du, we know what x is. Let's just circle it here. I'm not going to write x du because I know e to the u is the same thing as x. So I'm going to write, instead of dx, I'm going to write e to the u, because e to the u is x, e to the u du. E to the u du. Okay, so we successfully rewrote this integrand. Now let's keep going. Did this help? And it actually did, because these have the same exponent. It's not as tricky as it looks. So let's rewrite how this looks really quick. Just to save some writing so you don't have to keep writing this limit, let me just work on the integrand. This is e to the u over 2 to the u. So from your rules of exponents, if the exponent in the numerator and the denominator are the same, you can kind of think of that like factoring out. And so that's e over 2 to the u power. Okay? And so now, let me remind you what happens here. So let's recall some facts from Calculus 1 really quick. Because notice what you're doing, you're integrating this. You're integrating this. This is not base e anymore. This is base half of e. So from Calc 1, so just say recall, when we learned about derivatives, we learned that the derivative of a to the x was a to the x, just like derivative of e to the x would be e to the x, but because the base is not e, it's times something extra, specifically natural log of a. Okay, so this is not base e, this is base half of e. E's there, but don't let that make you think this is e. This is just some other number. And so we have to use this a fact, okay? So when we're integrating, we're going to do the opposite of this, okay? We're starting with the derivative and we're finding the antiderivative or the original function. So let me also remind you what we learned at the beginning of this class. And specifically, this was on one of your tables of a bunch of integral functions, integral values. So recall from table 8.1, the integral of a to the x, let me just separate that there. A to the x is going to be a to the x, but you have to divide out that natural log of a, and then technically plus c. Okay, so I just want to remind you this, and then where it came from, this one, that it came from this. Okay, so now that is all going to be used for here. Okay, so let me erase and get us ready to use that fact. Okay, so let's get this out of the way. And we can probably move some of this too. Okay, I want to leave what u is because I'm going to have to resubstitute. So we have our limit as b goes to infinity. We are integrating, let me make it really clear because I kind of just squeezed it down here. We are integrating e over 2 to the u power du. X was from 1 to b. Okay, so based on our fact here for integration, we know that this is the same base, e over 2, to the same exponent. It's like a, with the same exponent that it used to have. But then we have to divide by natural log of the base. So natural log of e over 2. Okay, evaluated from x is 1 to b. Okay, so we integrated. We're done with the integration. Let me just move what u is. U was natural log of x. Let's go ahead and resubstitute so we can plug in these boundaries. So that gives us the limit, so technically I should have put the limit here, but I'll put it on this step, as b goes to infinity of e over 2 to the ln x power over ln e over 2 evaluated from 1 to b. Okay, now this might look like we have some variables going on. The only variable at this point is x. This denominator is just a number. You can type this in your calculator and this is just some value. So let's plug in b. So we have our limit as b goes to infinity of e over 2 to the natural log of b over natural, actually let's factor out this denominator. It might just make it a tiny bit easier for us. Let me move this. I think we're good with that. Okay. So I'm going to factor out this denominator just to not have to keep rewriting it so close to what we're working with. So 1 over e, 1 over ln e over 2 times our limit as b goes to infinity of, and let's see if we can do this all at once, e over 2 to the ln x power, but we're going to plug in b, minus plugging in 1. Okay? So ln b minus e over 2 to the ln of 1. All right. Let's start with the back one over here. Also from algebra, let me remind you what ln of 1 is, natural log of 1. Okay? Natural log of 1. For the rest of your life, natural log of 1 is 0. Okay? Real quick, why that's true? This is saying log base e of 1 is 0, so this is saying that e to the 0 power is 1, which is true. The only way to turn 2.718 into 0, or sorry, into 1, is if the exponent happened to be 0. Okay, so that's just 0. And then anything to the 0 power here is going to just be 1, other than 0 to the 0. So that whole term is just, I said 1, I wrote 0. That whole term is just 1. Okay, now here, what happens when we plug in a very large number? Natural log of a very large number is a very large number. And if we raise this number, e over 2, if you plug that into the calculator, actually let me just plug that in really quick. What's half of e, okay, is 1.4. Okay, so this is about 1.4. So you're raising 1.4 to a very large power. It's getting bigger. So this whole term here, this is going to grow. It's going to go to infinity. Okay, so look what's happening here. And I know this is not technically proper notation, but it's going to get the idea across. Okay, I have this number times infinity minus 1. Okay, and the improper part is that infinity is not really a number, so officially I can't compute this. But this is saying some small number, some small amount, times infinity, and then take away 1. No matter if I divide by this number and this ln e over 2 and subtract 1, it's still huge, it's still infinite. So this is infinity. Okay. So this integral did not converge. It went to infinity. It kept growing, it diverged. So we can conclude, let's write it right up here. So we can say that since the integral from 1 to infinity of 1 over 2 ln x diverges, this went to infinity, then so does our series. Then the series from 1 to infinity of 1 over 2 ln of n also diverges. All right, and that is the integral test.